Up to now, we've seen the concepts and the mathematical ideas we need to reason about performance. Let's now take a step back and think more about how can we increase performance. There are basically two ways to do it, but with a very big caveat. So the caveat is intractable problems, and I'll talk about that in the next video. Let's talk now about the two ways to increase performance, which are new processor hardware. In fact, we are in a very interesting time since the speed of processor hardware is somehow still obeying what's known as Moore's law, an empirical law that tells us that speeds are increasing of new systems released over time. This is still true, even though people were a little bit worried in 2004 since the clock speed of the system has kind of leveled off, but Moore's law is still a valid law and it will remain valid for some time to come. So that's the first way to increase performance. Wait and buy next year's faster machine. The second way is program optimization. So instead of using a naive, stupid algorithm, use a faster, clever, but perhaps more complex algorithm that goes faster and improves performance. But be careful. This is fraught with dangers, and in fact, the lesson, which was immortalized by computer science pioneer Donald Knuth in the phrase, premature optimization is the root of all evil. So we'll talk about that. So let me talk first about Moore's law. So Gordon E. Moore, one of the pioneers of integrated circuit design, first observed this law in 1965. So almost for 40 years this law has been holding. And what it says is that the density in terms of transistors per square centimeter of integrated circuits doubles around every 2 years. So how can that be? How can that be an empirical law? It's not a law of nature. In fact, the origins of the law have been studied, and there are both economic and technological origins. So there is an economic drive to increase performance, but technology has to allow it. So there is some kind of economics and technology behind it, but the law holds and will continue to hold for a few more years. There is another version which says performance doubles around every 18 months. This is not Moore's law. It's actually a widespread interpretation, but it's false, but it seems to be holding as well. On the other hand, even though the density is improving, performance is improving, clock speed is not improving in the same way. So we're currently at a plateau. So clock speed has been improving in the past, but it leveled off around 2004 with the current silicon-based technology. Perhaps with new technologies later it will take off again, but for the moment it's not. But circuit density is still increasing, performance is still increasing, and the increase of circuit density is leading to multi-core processors. This started in the early 2000s, so now 4, 8, and the number of cores will continue to increase for the foreseeable future. So here's a graph. So this graph comes from Intel, Wikipedia, and other sources on the internet. So in the green curve here is Moore's law. It's transistor density. So this gives me thousands of transistors. So for example, in the year 2008, there were CPUs, chips with around 1 billion transistors. And this is still following Moore's law. The dark blue line here is clock speed. Notice that this line has leveled off around 2004 at around 3 gigahertz. If it would have increased, it would have been 30 gigahertz in 2010, but it's clearly not. It's still around 3 in 2014, and probably will stay until we go into another technology. There are two other curves here, so power consumption in watts and performance per clock cycle. So these have also kind of leveled off. But the main one here, the circuit density, is still increasing. Let me say a few words about optimization. Okay, when the performance of an algorithm is insufficient, we can improve it. The basic idea, we can use a better algorithm, so a specific technique, or we can use a general approach that can help many algorithms. So developing a better algorithm is usually not so simple. It requires thinking, which is widely known to be difficult. General techniques might be easier. So a technique that often helps is called memoization, which means to keep the results of previous computations around so you don't have to recompute them. So, simple example, if you take a simple Fibonacci algorithm, the exponential version, and you memorize the results, it becomes the linear time version. So the problem with this approach of improving the algorithm is that it only works up to a certain point. After this point, the improvements get smaller and smaller with more and more complex algorithms, and the complexity goes up very fast. So there's an effect of diminishing returns, and this was noticed very, very early, that in fact most of the time you don't need these complex algorithms. Only small parts of a program actually are where most of the time is spent and actually might be able to use these more complex algorithms, but it's very hard to predict where these points are beforehand. You have to measure and profile programs to find out where they are afterwards, and only if you see performance bottlenecks. So this has been pithily summarized in the phrase premature optimization is the root of all evil. The idea is never to do optimization before you really have a manifest need. Always start with a simple algorithm.